Alright. Okay, how's everybody doing? Good, good, good. Everybody saw or can access the homework? Okay. Michael caught a typo, so I fixed it that night, so it's updated. But if you have questions or anything, let me know, okay? It's pretty straightforward. I mean, it's applying the rules and getting your hands dirty by, taking all those traces and, trying to get it down into the simplest form that you can. We're going to go through a couple more calculations today, and then next week I'll try to discuss QCD. So we'll try to do non-abelian gauge theory. Okay. I won't be able to get around to full standard model and Higgs mechanism, but once I introduce you to non-abelian gauge theories, and then you go back in the summer and you can see we worked out the Higgs mechanism then towards the end of the semester, I believe. So those notes are in the Dropbox. But anyways, so we'll have a good. We've got to get 3 more days to cover.
QFT 3?
No. No. I need a year off from this class, man. I need a year off from everything. No QFT 3. I thought about it before, I didn't teach it like beyond the standard model stuff, but I've never gotten around to it. I always have to teach quantum. Okay, so what did we do last time? I forgot my notes. So last time we did. Oh, okay. So we did. Okay. Well, we did constant scattering at the end. What did we do before that?
Mandelstrom variables.
Oh, okay. So
and crossing symmetries before that.
Yeah. Okay. So we previously calculated. E plus E minus goes to U plus B minus, right? And then last time we introduced this idea of crossing symmetry, where you can get, an amplitude for one process by crossing, initial state particles and the final state particles of other processes, okay? And sometimes, you have to be careful with the signs, SIGN signs, when you cross fermions. But it's a very, very useful tool, and you'll see today that we can use it in other processes as well. Okay, get rid of this Java. Okay, so what I want to do today is talk about, just kind of finish up our discussion on constant scattering. I think last time we just started by writing down the amplitude. Okay, and then we'll derive the cross section, and this cross section has been known for almost 90 years now, but we'll see how you can get it in QFT. It was obviously not computed in QFT 90 years ago, but okay. All right. So last time, so these notes this is all PowerPoint because I can't write anymore. My hand's just gone. So so last time we ended by considering Compton scattering. Okay, so this is the case. Typically, Compton scattering is the electrons at rest, and you're bombarding some surface with high energy photons or gamma rays or X-rays or whatever they used back in the old days. All right, and so you have two different processes that contribute to this guy. Okay, so I think these diagrams are probably drawn in a slightly different form than the way I would draw them. Okay, and the way I drew them last time. So in this case, you have the photon. Pointer. So you got the photon and the electron coming in, and they're going through an S channel. Okay, and producing final state photon and final state electron. And in this case, this is a U channel diagram. Okay, so we had S and U channel diagrams, right? Is that what we had last time? Okay, good. I just want to make sure I called it U and not T. All right. So this is the U channel diagram. So a lot of times you'll see in these processes that have, a single or even sometimes a double fermion line. Remember this is from Peskin, so time is flowing upwards. Okay, so that's why it looks different. But a lot of times you'll see these processes that have fermions, both in the initial and final state, drawn as a straight line, right? Instead of drawing it like a usual S channel diagram, T channel diagram. And in fact, if you look in Srednicki, that's the only way he does it. Okay, and it's for just kind of housekeeping reasons. Okay, but I always like to draw them as S channel or U channel because then it's easier for me to tell what channel, what type of diagram it really is. Okay. So we used our Feynman rules from QED, right? And we wrote down the amplitude. So this process here, the S channel, is going through this guy, right? And then we have to add in this term, which is coming here. Okay. And you notice that there's no, you can check the relative sign, right? Because sometimes when you have fermions in the process, there might be relative sign differences between two diagrams, but in this case, there's no sign difference. Okay. And I think we got to the point where we wrote this down, and we tried to, before you go off and square stuff, it's always, always, always good to try to simplify stuff as much as you can, right? And we saw a little bit of that when we computed the polarized cross sections, right? We saw, you had these big long traces that had a couple of gamma 5s in it, and we saw that you could simplify things by contracting those gamma 5s and doing some different stuff, okay, before you square it. Because once you square it, and if you have, expressions that look like this, all hell's gonna break loose, okay? It's, if you're trying to do it by hand. If you're doing it, with a computer, then who gives a shit? You can do it however you want. Just punch the computer. So we used the fact that photons are massless, right, to simplify these denominators, and we used the Dirac, not the Dirac equation. Okay, so here's the expressions that we used, right? So we simplified those denominators by using the fact that the photon's massless, so k squared is 0, and the p squared that comes out of here is m squared, so m is the electron mass. And those two masses cancel off, so all you get is this little dot product. Okay?
And that we consider photon massless, we consider that they are real photons.
Yeah, because these are external state photons. Okay, so yeah, so they're on shell. So yeah, so these denominators just reduce to these nice little dot products. And then we use the fact that, so we wanted to use the Dirac equation to simplify some stuff. And in order to do that, we have to pass these operators that look like P slash plus M. We had to pass them through some gamma matrices. So if you look back here, you can see like this guy, this P slash plus M has to go through this gamma nu to get to the U. Okay. So we worked through that. So the M obviously goes right through the gamma matrix, but you have to anti-commute this P slash through the gamma nu. And after a couple steps, this thing right here will give you 0. And so all you get is this one term, the P nu term. And I think we left off with the amplitude in this simple form. Okay, simple, again, Peskin's words, not mine. Okay, so you can see we factored everything out. So we got the coupling squared and these polarization vectors coming from the external photons. And then we've got our fermion string here going from U bar to U. Okay. So what we want to do is, the next step is to compute the matrix element squared. Right? So we need to take the complex conjugate of this, which is not hard. Right? But when we compute the matrix element squared, we want to sum or average over the spins. So we average over the initial spins and sum over the final state spins. And so what we need to do is work out how do you do this for photons. Okay, we know how to do it for fermions, right? We have these spin sums, the U bar. And when you sum over them, they give you a P slash plus M or something like that. So we want kind of an analogous relation for the photon, right? How do we sum over the polarization vectors? Okay, so like I said, so here's the spin-sum relationship for fermions. So you sum up these spinors, right? You sum over the spins of these spinors, and it gives you the basically the Dirac operator, P slash plus M. Right? So we want something similar, and it turns out that there is something very similar for the photon case, and that is when you take when you sum over the polarizations of a polarization vector and its complex conjugate. Okay, so these have the same. These are coming from the same photon. Okay, so this is coming. So I just don't want you to get confused. Because see here you have epsilon and epsilon star, but they're coming from different photons, right? This one's coming from the one that has momentum k. This is the guy that has k prime. Okay. But here, you're taking the matrix element squared. Okay, so these guys would have arguments of k and k. Okay, so because you've taken the complex conjugate. So that's where this star comes from. Okay. And so the relationship is when you sum over these polarizations, you can make the replacement of this thing with just minus g mu nu. Okay. Notice that I'm saying make the replacement. It's not an equal sign. Okay. So it's making a replacement, right? But what you can show is that this replacement is valid as long as this stuff is being dotted into the rest of a QED amplitude. And what I mean by that is that this stuff is being dotted into stuff, so you have a scalar. Okay, so you don't have any open indices in your amplitude. All right. Okay, so as long as this stuff's being dotted into the rest of a QED amplitude, or could be QC. Well, let's just say QED for right now. You can make this replacement. Okay. So we can kind of derive this relationship, and to do that, we're going to consider an arbitrary QED process. So that's what I have drawn here. All right, so there's some blob, and inside this blob, there's all kinds of stuff that could be happening. There's all kinds of stuff that can be happening inside of here, but the important thing is the external legs. Okay, the number of external legs. So you can see there's a number of fermions and there's some number of photons. Right, and luckily I didn't give you this diagram to compute for the exam. But anyways, this thing we can write as an amplitude. This amplitude is going to depend on the momentum of this photon, right? This photon coming out of here, k. It'll depend on the other momentum as well, but we're just trying to extract this one guy right now, okay? And so what I can do is I know that I've got an external photon. It's a final state photon, right? Because it's leaving the rest of the diagram. And so what I can do is pull out that epsilon star factor that comes from the external final state photon, okay? So what I'm going to do is rewrite this amplitude that I know is a scalar in terms of the polarization vector coming from the final state photon, and then whatever's left over. And I know whatever's left over has to carry an index mu because these two things dotted together within the scalar, okay? And these photons always come with these polarization vectors. So we're still being completely general. So this is the amplitude, right? So when we take the matrix element squared, we would take this thing starred, right? And we would replace mu's with another index, right? Another dummy index just to be safe, right? So when we take the matrix element squared, we would plug in this, expression that we've kind of broken it apart now, right? And when I square this thing, I get the epsilon mu star and the epsilon nu that's coming from the complex conjugate, and then here's the m and m star, okay? And they both depend on k. Okay, so nothing mysterious yet. Just taking some arbitrary QED process and stripping off this polarization vector, okay, and then taking the matrix element squared. Right? What I'm trying to get to is to see that this replacement that I wrote down and just kind of pulled out of a hat actually works. Okay? When I'm summing over polarizations. Okay. All right. So when we set up our coordinate system, we're free to put the axes wherever we want. Okay, and a lot of times you can use this to your advantage. So in this case, what we're going to do is we're going to align the z-axis so that it's along the k direction. Okay, and so what that's going to do is allow me to write the 4 vector in a very simple form. Right? I know it's a photon, so it's got to be massless. If the only 3 momentum is along the z-axis, then the x and y components are 0. Okay, and what that allows me to do is to write down the transverse polarization vectors in a very simple form, right? Because I know that when I dot these two together, I have to get 0, right? And I know that there's 2 transverse polarizations, right? So that one in the x, they're going to be in the xy plane, right? So why not just align them so that one of them is along the x direction and the other one's along the y direction, okay? And that satisfies all the constraints, that you have. Okay. All right. So what that does is when we compute this thing, right, and we go back here and we see that we're summing over the polarizations here, right? So the only contribution that we're going to get out of this thing are contributions from 1 and 2. Right? So epsilon 1 and epsilon 2, the transverse polarizations. Okay. This is coming from the fact that we know right now, physically we know that the photon doesn't have any longitudinal polarizations. Okay, so all we're considering are the transverse polarizations. Okay, so everybody see how just by using these polarization vectors, you can go from this guy at the bottom here to this guy.
Yeah, it picks out.
It's just picking out the mu equals nu terms, right? Okay. And there's only 2 of them, 1 and 2. Okay. So this is M1, not and M2, not M squared. The squared is out here. Okay. All right. So this is where we want to make contact with, what our understanding of, where the photon comes from and how it interacts. Okay. And so if you go back to when we first started talking about the Dirac equation, and we started talking about the QED interaction and things like that, we talked about the fact that external photons are created by this interaction. Okay, so what we would say in the business is that this J mu is a source of our photons. Okay, and this J mu is just the regular Dirac current that we worked out. I think you guys might have had homework problems on it. But J mu is it's just the vector bilinear, so it's psi bar gamma mu psi. Okay. So this is the form of the interaction, the QED interaction. Okay. And so what we would expect, right, given this information and what we know about having stripped off the polarization vector, is that this matrix element, so this is the one without that epsilon, right? So I take the position space version of it and I'm doing a Fourier transform, okay, because I want to work in momentum space. Okay. So we have this general expression. Okay, so I'm taking, this is just the matrix element. I have some interaction here between the initial and final states. And we also know that for this current, that we know that this current is conserved. Right? In other words, that the derivative of this thing is 0. Okay. So what we can do is put these 2 pieces of information together, right? And what we see is that if we plug this in, right, taking the Fourier transform, this del mu is going to become a factor of the momentum mu. All right. And the fact that this thing is 0 tells us that if we take this amplitude mu, where we've stripped off the polarization vector, And actually, we replace the polarization vector with the momentum vector, the 4 vector, that this dot product is going to give us 0. Okay? And this is a very, very, very important relationship. Right? It's telling us, like I said, the full amplitude vanishes when we replace the polarization vector with the momentum vector. Okay? And this would have happened if we had taken any of these photons, right? And done the same analysis. Okay? And this is called the Ward identity. Okay? So anytime you have a process that you're computing that has external photons, it's always a good check once you've gotten the amplitude written down to do this check, right? To take your epsilon and replace it with momentum, and make sure that the amplitude vanishes. Okay. And you can do that for the Compton scattering amplitude. I don't do it here, but it's not that hard because once you do it, you'll see that this K mu gets dotted onto a gamma mu. All right, so it becomes a K slash. And then you just have to move some K's and K primes around, and you'll see minus signs pop up, and everything will cancel and give you 0. Okay, so it's always a nice check that if you're computing something that has a mass of spectral boson, to use this Ward identity to check your what you've written down. Because if it's not 0, then it's something wrong, right? Because the Ward identity is rock solid, and actually. If you look at Pesca in section 7.4, there's a proof of it. Okay, I don't feel bothered wasting time proving stuff. All right. Okay, that's what I was just saying. That you can actually do this replacement, and in a few lines show that amplitude that we've written down gives you 0. Okay. All right. So having now worked out or now we have this kind of this. Ward identity in our pocket or in our toolbox or whatever you call it. All right, we can go back to the calculation of the Compton scattering amplitude, right, or the matrix element squared. Actually, we want to go back. Sorry, before that, we want to go back to our derivation of polarization sum. Okay, so we're trying to show that this relationship is valid. Okay, this replacement of summing over polarizations. And replacing with minus G there. All right, so for us, we've aligned, so what we've done in this thing, all right, we aligned our axis so that the z-axis is pointing along this k direction. Okay, so that tells me that the k vector, again, only has components in the z and then in the energy component. Right? So when I dot k mu into m mu, I know for sure that the only non-zero, or possible non-zero pieces are going to be from the M0 piece and the M3 piece. Okay, just using the normal dot product rule, right? And what I see is that this implies that the M0 part of the amplitude is equal to M3 part of the amplitude. Okay. And this is not a surprise, and I'll show you why in just a minute. So what we can do is now use this fact, right, that M0 is equal to M3, right, to rewrite. So we had gotten to this point, right, by taking the sum over the transverse polarizations. But now I can add and subtract M3 squared and M0 squared, right, because they're the same thing. Right? And now when you look at this thing, this is exactly like minus G mu nu. Being multiplied by m mu and m nu star, right? So this minus sign you pull out, and then you have the 0 minus the 1, 2, and 3 components. Okay, and that's the metric tensor, right? And it's in our convention. Okay, so you compare this side to this side, right? And you can see that when I'm summing over polarizations, it might not be an equals, you might not be able to write down equals, but from comparison, you can see that I can replace the sum with just minus G mu. Okay. All right. And so it's valid. Okay. And the fact that M0 equals M3 is not a surprise because like I said, we don't want longitudinal or time-like polarized photons. And so what that M0 equals M3 is telling us is that those guys will always cancel off each other, right? So we never have to worry about those. Okay? So the way we've constructed our theory is such that we only have transverse polarizations. Now, that won't be the case if you have massive vector bosons. There you do have longitudinal polarizations, okay? So that it gets a lot more complicated. All right. Okay, so now we know how to sum over and average over the fermion spins, and we just worked out how we can sum over and average over photon spins. Okay. So now we can actually compute the matrix element squared for Compton scattering. Okay. So once you have these things, these tools in your pocket, Peskin says the rest of the calculation is straightforward. Okay. So I thought about just stopping there and turning off the projector and then going home, but I'll cover it just in case, for my own sake. All right. So when you take the matrix element squared of this thing, it's easy enough to get it into the form of a trace. Okay. So you can just, a lot of times this stuff, that was in the amplitude, you can just write it as some thing, just write it as shorthand notation, whatever. So you'd have a U bar something times U, right? And I take the matrix element squared, and that's going to give me these P prime slash plus M and the P slash plus M. And these G mu rho and G mu sigma are coming from the sum over the polarization of the photons. Okay. And so notice another thing too is that I'm averaging over the initial spins, right? And the fermion, the electron obviously has two spins up and down, and the photon also has two different spins, right? It's based or polarizations, so it's the two transverse polarizations. Okay. When we get to QCD, we'll see that there's more degrees of freedom here that you have to average over, okay, or sum over. All right. So in these types of diagrams, especially where you have multi-diagrams that you're summing together, it always pays to take your time and be organized, all right? Because what you would see is if I take this thing and I multiply it out, I square it all out, it's going to be a freaking mess, okay? So it's always good to try to break it into small, bite-sized pieces, right? So pieces that you can handle, and then put it all back together at the end of the day, okay? All right, so I'll show you how one way you could organize this calculation, right? So this is what we get when we take the matrix element squared and then sum and average over the spins. Okay? And so what I'm going to do is schematically, I'm going to write this in terms of four terms. Okay? So you can see that when I square it out, I'm going to get this term squared, and then the cross terms. Okay? And so I'm going to call those terms kind of schematically, the denominators aren't the problem, it's the traces, right? So I have the trace 1, trace 2, trace 3, trace 4, right? And these guys are, it goes without saying that they're complicated traces, okay? But luckily for us, and this is where it's worth taking time to look at what you have, right? And take a breath and, maybe walk away, go have a cup of coffee or something like that, and come back and look at it because a lot of times you'll see, different symmetries or, other tricks you can use, okay? So they're complicated traces, but there's some tricks that we can use to reduce. And one of the tricks is that, if you wrote these out, you would see that this trace 4 is the same with trace 1 if I replace k with minus k prime. Let's see if we can see that here. Because let's see, k prime, then there's the overall minus sign. So you can see that if I go from k, so this would be the trace 1 piece, and this is the trace 4 piece, right? And so you can see k slash, if I replace that with minus k slash, and I replace k with I replace K slash with minus K prime slash, and case K dot K down here with minus K prime, that I can get to this guy, right? The indices are different, but the structure is the same. So that tells me that, okay, I don't have to calculate 4, because if I calculate 1, I can just make that replacement and that'll give me 4.
And that comes from the crossing extension.
No, I don't think it's coming from crossing somebody. It's just from the fact that,
It's just an observation.
yeah, you just notice that it has the same structure. Also, remember that you have all these tricks you can do with the gamma matrices. And one of the tricks that I just kind of showed you guys is that if you have gamma matrices in a trace, you can reverse the order of the gamma matrices. And in the trace, and the trace is invariant of that flip. Right? And when you do that, you can see that 2 and 3 are equal. Right? So let me go back here, and so you can see that if I reverse the order of the gamma matrices and keep track of the indices and stuff, you can see that 2 and 3 are equal. Okay, given that fact. Okay, so these two terms will sum up. Okay, 2 and 3. So they have they have different denominators. No, 2p dot k prime. Yeah, so these two terms will sum up. Okay, so at least out of these 4 complicated traces, we only have to compute 2. Right, you can pick which 2 you want. I'll just take 1 and 2. Right, and then from there we can get 3 and 4 just by using this trace that we pointed out. Okay. All right, so let's look at one of these traces. Okay, so let's look at trace 1. Right? And you look at this thing, and it's a mess. Okay, when you square this out, there's 16 possible terms inside this trace. Okay, but luckily for us, half of them, so 8 of them, contain an odd number of gamma matrices. Right? And as soon as you see that, you should say, I can drop those terms. Okay, so those vanish. But unfortunately, we still have to evaluate the other 8, okay? So let's consider one of these guys, and I'll show you what you can do, okay? So if you look at this guy, you see a couple things, right? So I see that gamma mu and gamma nu are being contracted on these gammas over here, right? So instead of taking the trace of 1, 2, 3, 4, 5, 6, 7, 8 gamma matrices, which I don't even know how to do, I would take these gamma mu and gamma nu and move them over and contract them on these guys before I take the trace. Okay, so that's what I've done here, right? Or that's what we've done here. And you can see the minus 2p prime and 2p coming from passing these gamma matrices through this p, this guy. Right? And I think what he's done is used. So you use the cycle. What's the word I'm looking for? No, he's just cycled this gamma mu to the front, all right? So that p prime slash is between the 2 gamma mu's. Okay, so that's where this p prime slash comes from. That's where this p slash comes from. Okay, and then, so what is he doing? So now you have p prime slash k slash p slash k slash, right? So you can contract these 2 k slashes, right? That'll give you k squared. And you've seen that relationship before. So I can pass this k slash, or I guess this one through to the left, right? And that's going to give us the second line, right? And then I can, like I said, I can contract these k slashes on each other. That gives me a factor of k squared. And now I have this term, so I'm just doing the trace over these 2 guys, right? Because this guy will have 1 p slash left over, but I know the trace of 3 gamma matrices is 0. Okay, so once I contract that k slash out, I'm only left with this term. Okay, so you can see that it's just a trace of 2 gamma matrices. Okay, and so I know how to do that. It's just the p prime dot k, some factor of 4, right? But the point is that I've taken a trace of 8 gamma matrices that, if you fed it into a computer, you could do it, but by hand, it would be a beast, right? But by using these tricks of contracting gamma matrices, contracting like, P slashes, K slashes, you can whittle it down to something that you can manage. Okay? So that's just one of these terms, one of the 8 terms in just the one trace. Right? But you can go through, and once you do one of these, you can start to churn them out pretty fast, right? And so you can use similar contraction identities. You can use some Dirac algebra to reduce some stuff. And what you find is that each term in this trace 1, can be reduced to a trace of no more than 2 gamma matrices. Okay, so it behooves you to do some work before you try to take these traces. Okay, and when the smoke clears, you find that this trace 1 can be written like this. Okay, well, this isn't that bad, considering what you started out with. Okay. All right. So what you can do now is you could leave it in this form, right? Or you could try to simplify it even more by introducing the Mandelstam variables, right? And I'll tell you from experience that sometimes introducing ST and U does simplify it, and sometimes it doesn't. Okay. And sometimes using that relationship where you use the S plus T plus U equals the sum of external masses to replace U or replace T or replace S, something like that. Sometimes that helps. Sometimes it just makes it uglier. Right? It's a lot of trial and error. Okay. They'll all be the same, but you're trying to get the expression down as far as as small as you can. In this case, it does simplify it some. You can replace all these dot products with ST and U, corresponding ST and U, and you can get it down to something that looks like this, which doesn't look half bad. Right. The cool thing is that this right here is basically the propagator, right, for the S channel diagram. So what you'll see is that this guy will cancel off the denominator in full amplitude squared, or at least part of it. Okay, so that's trace 1, and we've seen that if we take K and we replace it with minus K prime, we can immediately write down the trace 4, so that's what we do. And so when you do that, when you take K to minus K prime, it's basically you're exchanging S and U, right? Okay, and then finally, I'll leave it for you guys at home to do. You can do the calculation of the trace 2, right, and then use the fact that 2 and 3 are equal, and you find this guy. Okay, so again, just it's just some linear combination of masses and ST. Okay. But in the end, when you put it all together, it's actually, for the case of Compton scattering, and actually if you want to do an analysis where you're looking at this in a particular frame, right? So you want to look at scattering angle or energy dependence or whatever. It's actually better to just leave it in terms of the dot products. Okay. So when you sum up 1, 2, 3, and 4, the matrix element squared in terms of dot products, you can simplify it down to something that looks like this. Okay. All right. So we've got the matrix element squared. Now we just need to plug that into our cross-section formula, right? We got the cross-section formula that you can go to the back of Peskin and look up, right? But before we do that, we have to specify what our frame is, okay? And like I said at the beginning, Compton scattering is typically done in the lab frame, right? Because this is what Compton scattering is. They're basically bombarding some surface with photons, right? And they're looking for looking at the scattered electrons or the photon. I can't remember what they measured actually. But this is the initial state. So you have the initial state where the electrons in the rest frame, right? So if you're in the electron's rest frame, I should say, right? So its forward momentum is really simple. It's just the mass and zeros for the rest of the components. And the photon's coming in with energy omega, right? Or remember, we've set h bar to 1, so energy and frequency are the same units. Okay, so this is the frequency, but it's also the energy. So it comes in, it scatters off the electron, and you end up with some k prime, right? So you can see here that I'm being completely general, but I'm using azimuthal symmetry, right? So I know that I can line this up so that I only have one component in x, and the y component I can set to 0, and the z component is just the cosine part. Okay? And then finally, the electron, p prime, which is, just write it in terms of general variables. Okay? And so what we want to try to do is use this picture, right, and compute all these dot products to put the cross section in terms of the lab variables, which are the energy of the initial photon, the incident photon, and the scattering angle theta. All right, but before you do that, so you go back and you look at this here, right, and you have this omega prime, right, and you don't know what that is, right? You could solve for it by writing down conservation of energy, conservation of momentum, and all that stuff, and actually solve for omega prime. And with Mathematica or something like that, it's not that bad how you can do it. But you can actually compute it using a trick. Okay? And the trick is to take the on-shell relationship for the final state electron. Right? So the final state electron has mass m, so m squared would be p prime squared. Right? And then I can use conservation of form momentum to rewrite p prime in terms of p and k and the minus k prime. And now I square this out, okay? So I get this p squared term, and I would get some k squared terms, but any k squared terms, those are the photons, so those can go to 0. Right? And then I get some dot products between p and k prime, and then dot product between k and k prime. Okay? So now I can go back and use these guys, right, the expressions that I wrote down to compute these dot products. And so what I get is some relationship that says m squared is equal to m squared plus blah, 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 right? I can see that I have omega prime in here, and that's what I'm trying to compute, right? It turns out that you can actually rewrite this relationship like this. This is not what we want, but I just wanted to point it out. So this is 1 over omega prime minus 1 over omega. Right? So this is like the difference in wavelengths, right? Remember, the wavelength goes like the inverse of the frequency, okay? And it goes like 1 minus cosine theta. And so if you remember back to your modern physics class, or whatever class you took, where you first start to encounter these 20th century physics, you might remember this. It's called Compton's formula. Okay? So that's that, right? And Compton came up with it in a very different way. Okay? We're getting to it from quantum field theory, right? But now we can solve for omega prime, right? That's what we were after. And now we've got omega prime in terms of stuff that we know, stuff that we can measure. So the incident energy of the photon and the scattering angle. Okay. All right. The phase space. The phase space takes some work. Okay. The phase space. This is why we like to work in the center mass frame. Because the phase space is a lot easier to work with. Okay, but here you can do it. It's not that bad, right? So you can write down. This is the initial. So this is the equation you would write down, and now it's a matter of using these delta functions to evaluate some of these integrals, right? So I can use the three pieces of it to do one of these k prime or p prime integrals, right? And so I'm using it to do the p prime integral. So it leaves me with k prime, and k prime I'm rewriting in terms of omega prime. Here's the integral of the solid angle. And so I'm left with this mess inside of the remaining delta function. Okay? And so this is where you want to use that famous formula for the delta function where because you want to evaluate it this integral over, you want to evaluate it for this integral over omega prime, right? And you see omega prime is in three places here, right? So you have to use that relationship that the delta function of a function of some variable that you want to integrate over, right? And that goes like 1 over absolute value of the roots of the equation or something like that. I can't remember exactly, but that's what's going on here. So as you go from the second to the third line, that's what he's using. Okay. And then finally, you can plug in your expression for omega prime, or you can use that expression to eliminate some of this stuff. And you get down to this form, right, which you can again use the relationship that we derived between omega and omega prime to get it down to even this form. Okay? And that's about as simple as you can get it. So that's the phase space. All right, so now we have the phase space, matrix element squared, so we can put all this stuff together and get the cross section. Okay? And so the cross section looks like this. So here's all the stuff coming from phase space, the other stuff in the cross section formula, and then here's my matrix element squared. And so remember, when we left our matrix element squared, it was in this form, right? And I want to evaluate all these dot products. And these dot products, a lot of them are pretty simple. So like P dot K, because remember P is the initial state electron, and that guy's at rest. Okay? So these guys, P dot K and P dot K prime, are really simple. And what you get in the end, when you evaluate all these dot products, is something that looks like this. So this is the differential cross section in terms of the scattering angle, right? And you can see that it goes like these ratios of the energies, the initial and final state energies, and then you have this minus sign squared piece. Okay? And like I said, you can get omega and omega. So like this ratio omega prime over omega, or the inverse, you can get it from this guy. And so you see that you can write it in terms of the electron mass and the scattering angle. Okay. So I just rewrote it here so I can reference it. Okay, so this is what's known as the Klein-Nishina formula. Okay, and like I said, it was derived back in the 20s, 1929. So that was before the invention of quantum field theory. So they obviously, did this in a very different way. Okay, and I wouldn't even want to venture at how they did it, to be honest. But anyways,
It's exactly the same.
yeah, it matches on to exactly what they got. It's spin average, which I thought maybe they probably didn't average. Or I don't know what they did, but it matches, yeah. Okay. And actually, back when they were calculating it, you can work in the low mass or the low energy limit, right? So you can basically take omega to 0, and what you see is that omega prime over omega goes to 1, and the cross section takes this form. And so you can reduce it down to this, right? And then I can integrate over cosine theta if I want to get this guy. Right? And this stuff should also look familiar, either from modern physics class or from E&M, because it's a familiar, I should put that quotation marks, Thomson scattering cross section. Right, so Thomson scattering, which is scattering classical electromagnetic radiation by a free electron. Okay, so you should be able to look in Jackson, go back, flip into the index of Jackson, look up Thomson scattering, and you should hopefully see these formula. Okay. Okay. All right. So that's it. So that's the cross section for Compton scattering. And like I said, the main result is that you match on to the Klein-Nishina formula, and that has been checked out the wazoo as far as comparing it to experimental results. All right. But before we move on, we can actually use the stuff that we have already computed to compute another cross-section, right? By using crossing symmetry. Right? So in Compton scattering, I have photon electron goes to photon electron, right? So what I can do is cross one of the photons to the final state and cross one of the final state electron to the initial state, and it becomes an incoming positron. And so I can use the stuff that we've computed to compute E plus C minus goes to photons. Right? This is called pair annihilation, or annihilation of photons. Okay? So this is the process. E plus C minus goes to 2 photons, right? And we have 2 diagrams. Again, remember this is from Peskin, so the time's going up. Okay, so we have a T-channel diagram. And because we have identical final state particles, we have to consider the U-channel diagram. Okay? But like we talked about last time, there's a one-to-one correspondence, right, between, say, this diagram and the diagram that you get from crossing symmetry and Compton scattering. Okay? So you can basically go back and trace the steps, but just make the replacements of, K with, K prime with minus K2 or whatever, okay? So we can, the main point is that we can use, so here are the replacements. So we can use our Compton amplitudes, there's an amplitude we computed, even the matrix element squared, and all we have to do are make these replacements. So P becomes P1, P prime becomes P2, and so on and so forth, okay? So you can see the minus signs coming from, this was the final state electron, now it's an incoming positron, so you have to flip the momentum. And now initially this was the initial state photon, but now it's a final state photon, so you have a minus sign here. Okay. And so you can take your Compton amplitude squared and make these replacements. And what you find is, again, it looks very similar to what we had before, but there's this overall minus sign out in front. Okay, and I'm guessing from what so this is the way you would see it. So these the electron mass is small, right? So if you take the massless limit, you can drop these guys, right? And what you can show is that this stuff right here, because it's a ratio of T and U type invariance, those will be positive definite. Okay. So one thing we haven't seen yet is that S is always positive and T and U are always negative. Okay. So what I'm saying is that in the massless limit, you drop these terms. You see this thing, which is positive definite, and you get this minus sign out here, right? And if you plug that in the cross section, you're going to get a minus cross section, which is not good. Okay. So what we do is we just and the sign basically is coming from the crossing of one electron. And Peskin says, just remove it. Just get rid of it. And when I read that, I was like, what? But then I flipped back, and earlier in the chapter, he justifies this minus sign, getting rid of this minus sign. So you can basically shift the phase of your V and V bar spinners to absorb this sign. Okay. So you can, it's justified. You can just drop it. Okay. All right. Because at first I had that, and I was like, you know what? If I just remove it, Hussein's going to call me. Okay. So I went back and tried to figure out why you can do that. All right. So this is pair annihilation into annihilation of the photons, right? And so this would work best in the center mass frame. Right? This is going to be really simple. In the center mass frame, so we got your electrons here, right? Electron coming in, positron coming in, and then your photons going out. So this is basically the same setup that we had for E plus E minus goes to U plus E minus, right? The difference is that now, these final state particles are massless, okay? But you can carry out these dot products and work out. You already have the formula for the cross section in the center mass frame, and you can put all this stuff together, and you get this. Okay, so this is the differential cross section for pair annihilation into 2 photons. Okay? And you see that you got it in terms of the things you can measure, which are the incoming energy of the electron and positron, and the incoming momentum, and the scattering angle of these photons. And so what you can do is you can take the high energy limit of this, right? So we're taking the limit where energy is much higher than the electron mass, okay, which is an extremely valid thing to do. And when you do that, that cross section reduces to this two-term thing, right? And it's really simple looking, and surprisingly, or maybe not surprisingly, when you compare this expression here, so this expression as a function of cosine theta is what's shown here as the solid line, okay? And the dots with the error bars are obviously data, okay? So what you see is that even at tree level, so not having to go to higher orders of perturbation theory, QED is extremely precise, right? So typically you wouldn't see this until, if you were doing QCD, for example, there you have to go to higher orders, right? Because the coupling is a lot larger, okay? So, but because of the smallness of the QED coupling, you get really nice results even at tree level. Okay, I don't remember what year this is from, but let's say it's from the 1970s. I don't know, but this is a really nice result. Okay, it gives you confidence that the experimentalists are doing things right. All right, so I'll end with that comment, and so next time what we'll do is we'll move on and talk about QCD. Okay, so I'll introduce not a billion gauge theories, and then I'll construct QCD. And the nice thing is that basically we can use almost all the Feynman rules we had before and all the mechanics and stuff that we worked on. Right, the only thing that's going to change are the Feynman rules, and there's some differences between the couplings, and those have consequences. But we'll talk about that next week. All right.
We should use SU3.
Yes. Yeah, so there's going to be interactions between, so what makes it complicated is the fact that the gluon, which is the analog of the photon, it actually interacts with itself.
Mm-hmm.
Right? It carries charge, color charge. And that makes everything much more nightmare. Yeah. And the fact that the coupling is big. So,
Yeah.
So radiative corrections play a big role. And those never make anything better. Okay. But we'll talk about that next week. All right. Okay. So let me know if you have problems or questions or anything with the homework / final exam. Okay. All right. All right.
Thank you.
All right. See you guys next Monday. Good day. Have a good weekend.
Do we get to the algebra?
I won't spend a lot of time on the algebra. I'll cover enough of it so that you can understand some of the relationships that you have for QCD, but I don't spend, even when I have time, I don't spend a lot of time on the Lie algebra just because it's hard. Yeah, and I don't feel comfortable explaining it. People aren't comfortable trying to understand it, and it just ends in really bad ways. All right.